Hey, what's going on, Math 1? Hope you're having a great day. This is Mr. Bainey, and let's take a look at lesson 14.2, Constructing Geometric Sequences. In the last lesson, 14.1, we looked at just understanding how geometric sequences work. So you saw the definition of what a geometric sequence is, or what makes it geometric, and that's having a common ratio, and then just how to get additional terms. So when we looked at our geometric sequences, we know that we divide a term by its previous term to get our common ratio, and then we use that to get additional terms. In this lesson, we are going to look at how to build the rules if we have a sequence. So it's definitely going to use your knowledge from last lesson of getting your common ratio. Okay, let's take a look at this example part B. Our geometric sequences have both an input and an output, and that's how we're going to start making our rules here. So we have our n is like our input, or like where it is in the term, or where it is in the sequence, and our f of n is the actual terms, the list of the terms. So our first term is 5, second term is 15, third term is 45, and so on. So we could write our sequence like this. It is 5, 15, 45, 135, 405, and going on forever. The first thing that we need to find is our common ratio. We use the letter R to show the common ratio in these sequences, and so we can take 15 and divide it by the previous term 5, and we get 3. That means our common ratio is 3. The first term is 5. So our recursive rule, we're actually missing the first part here. The book kind of skipped it. We have to start off with our first term. We have to say f of 1 equals 5. That's the first part. Then we say f of n, that's any term after the first term. So like to find the second, third, fourth, fifth term, and so on. We take the previous term, that's this right here, and then we multiply it by our common ratio, times 3. So remember that second part just says that we're going to take, like if we want our 6th term, we take the 5th term and we multiply it by 3. So this is going to make up our recursive rule. The part at the end is not, I'm not going to worry about it if you don't really write it, but that's just to understand that when we talk about n, we're starting at the second term, at 2, right? So to use that rule, we have to use it for 2, 3, 4, 5, 6, and so on. We can't use it for 1 because we say that f of 1 is equal to 5. Then we're going to write an explicit rule. And to do that, and to understand how this works, we're looking at how are we multiplying these numbers to get the term, okay? So I'm actually going to ignore these 5 times 3. So you can cross those out as well. For the first term, it's just 5. Okay, the second term, it is 15, but I'm going to write it like this. 5 times 3. That's equal to 15, right? The third term, okay, I'm going to take the previous one, which is 5 times 3. Right, that's 15. And then times 3 again. Then the fourth term is 5 times 3 times 3 times 3. Right? You can actually do it if you don't believe me, but that should give you 135. And then finally, the last one is 5 times 3 times 3 times 3 times 3. Should give you 405 when you multiply it all out. So what's the interesting thing we see here is that we have 5 times 3 to the 4th power. And we have 5 times 3 to the 3rd power, 5 times 3 to the 2nd power. Okay, working our way backwards here. 3 to the 1st power. And 5 is like saying 5 times 3 to the 0 power. Okay. In order to understand how these rules work, how we're building them, we relate our input. Look at the input of 1, our exponent is 0. Input of 2, our exponent is 1. Okay. Input 3, our exponent's 2. Input 4, our exponent's 3. Input 5, our exponent is 4. So seeing what that pattern is means that if I'm going to look for the 20th term, can you tell me what that exponent is going to be? How many times we're multiplying 3 by? And if our input's 20, that means our exponent's going to be 19. So our rule is this. F of n equals 5 times 3 to the n minus 1. Okay, n minus 1 means we're going one less. Let's take a look at your turns on the next page. I'll do the first one. You do it with me. You'll do the second one, number 6. Here we go. Common ratio. I'm going to take the second term, 14, divided by the previous term, 7. Common ratio is 2. Here's our recursive rule. I'm going to just use the letter R. That's recursive. F of 1 means the first term. What's the first term? 7. F of n. All right, now we're going to write down how do we get all the other terms? Well, we take the previous one, that's this, f of n minus 1, and we multiply by 2. That's it. We're done. Explicit rule looks like this. F of n, right, to get any term we want to, we're going to take the first term of 7, and we're going to multiply it by 2 a whole bunch of times. Right, so it's 2 to an exponent, and the exponent is always, whoops, not m, n minus 1. Because remember, if I'm looking for the 5th term, right, if I want to plug in 5 here, I'm going to use an exponent of 4. If I want the 20th term, I'm going to use the exponent of 19. If I want the 100th term, I'm going to use an exponent of 99. All right, number 6. This one right here. I want you to try this one out. And just as a little hint, the common ratio will be a fraction, right? And if you want to change it to a decimal, if the decimal terminates, go ahead and use a decimal. All right, so go ahead and try this one out. Pause it, give it a try, and then check your answer here in a few seconds. And here you see the solution for number 6. Our common ratio is 1/4 as a reduced fraction. I chose to divide our third term divided by the second term. Reduces to 1/4, or you can use 0.25. That's actually a nice little decimal for us. In the recursive rule, f of 1 equals 128. F of n equals f of n minus 1 times 1/4, or times 0.25 if you want to use decimal. The explicit rule, f of n equals 128 times, in parentheses, 1/4 to the n minus 1 power. The parentheses on that second one is important because it uses an exponent, and we want to make sure that exponent goes to both the top and the bottom of the fraction. So you have to make sure you have the parentheses there, which means you won't need it if you use a decimal. Okay. There are different ways to write this, but this is generally how you'll see it. This is how we write the rule just in its general form. All right, if you have other ways that you want to write this, there are some correct and some incorrect ways. Definitely, come in and show me, and you can have me check your work. Now we're going to take a look at our last your turn, and this one is going to have us write an explicit rule for the sequence using subscript notation. And they don't just tell us, the first 5 terms or the first 4 terms. They only give us 2 terms, but they're not next to each other. So let's just try to make sense of this first. The third term is 1/27th. The fifth term is 1 over 243, which means the first term, we don't know what it is. Second term, we don't know. Third term, right, is 1 over 27. Fourth term, we don't know. And the fifth term is 1 over 243. Okay. Explicit rule is just the rule where just only one equation or one function we write to find any of the terms. Subscript notation. Now, this is a weird place to ask for it, but we'll write it in subscript notation. It's fairly easy. Instead of using f of n, remember what we call that? We call that function notation. We're going to use subscript notation, and it looks like this. Subscript means that the n, our input, is a little bit lower and smaller than, you know, the A or the F or whatever you're using. And it's just where we're putting the input, right? So I would say, in this case, A subscript 3 equals 1 over 27. And that just means the third term is 1 over 27. Okay, going back to our problem here. I know that I have to take the first term times the common ratio to equal the second term, times the common ratio again to equal that, times the common ratio to equal that, and you get the idea. I keep going here, but I'm only interested in the last two that I did. What we're really doing here is, what is 1 over 27 times the common ratio to get the fourth term, times the common ratio again to get my fifth term. And we know what the fifth term is. The fifth term is this. Okay? So the question is, what's this? What do I have to multiply this by twice, right? Two different common ratios, or not different, but two of the common ratios to equal this. So this is just an equation that we solve. And what I could do is divide by 1 over 27, since it's multiplying with those r's. And when I divide, I get r squared, because r times r is r squared, equals 1/9. So that means the common ratio times itself is 1/9. And the way we get rid of the r squared and just have r is to do square root. And we get 1/3. Okay. And technically, if I was to just solve this equation just in general, it would be positive 1/3 or negative 1/3. But then it tells you that all terms in the sequence are positive. That means my common ratio will be positive. Okay? So just to double check, you could do 1/27 times a third, and that gives us 1 over 81, yeah. And then that times a third does indeed equal 1 over 243. So 1/3 actually works. And I'm going to backtrack. That's how we get our second and our first term. That means this has to be 1/9, and this one has to be 1/3. Just, right, we're dividing by a third going backwards. So here we go. Here's our first term right there. Here's our common ratio. Now they happen to be the same exact numbers, and that's okay. A sub n, subscript notation, equals our first term times the common ratio. Remember, use parentheses here because we're using an exponent, to the n minus 1. That is our explicit rule using subscript notation. And that's going to do it for this lesson. Hope it was helpful. Remember that in this lesson, we just know how to learn how to write our recursive and explicit rules. And that's it. Have a great day. Thanks for watching.